Hi guys, hope you're doing great. We're going to continue talking about kinetics, and if you remember, we had talked about differential rate laws and integrated rate laws. So differential is when you're comparing rate versus concentration. Integrated is when you're comparing time versus concentration. So if you're given a problem where there's time involved, you want to use the integrated rate law. If you're given a problem where rate is involved, then you want to use the differential rate law. So today we're going to kind of put together all the information we know about zero, first, and second order together. So that you kind of have a summary of the different orders. So zero order, remember, means that that your rate is independent of the concentration. So if you double the concentration, rate remains the same. Triple the concentration, rate remains the same. So for the differential rate law, the equation would be rate is equal to the constant times the concentration of the reactant raised to the 0 power. Now anything to the 0 is equal to 1, so you can rewrite it as rate is just equal to a constant. If you were to graph it, if you were to graph rate versus concentration, you would have just a straight line like this because the rate is independent of the concentration. If you were to graph concentration versus time, it would look like this, with the slope being equal to -k. For the integrated rate law, if you look at this and plug it into y equals mx plus b, you would get that your y would be the concentration of A at a given time is equal to your slope, which is -k, your x, which is your t, the time, and then B is the y-intercept. The y-intercept would be the initial concentration of A. So before you started the reaction, what was the initial concentration of A? I'm going to write it down here that this means concentration at a given time versus A naught is the initial concentration. Now, one more thing that we have not talked about is half-life. Half-life is the amount of time it takes for half of your reactant to be consumed, to be used and turned into products. So at half-life, we're going to call T with a little 1/2. That means half-life. And when you've reached your half-life, your concentration is going to be half of what it was initially. So your concentration at time t is going to be your initial concentration divided by 2. So let's plug these in to our equation here. So instead of that, we're going to plug this in. So concentration of A naught over 2 is equal to -kT plus the initial concentration of A. If you rearrange this, take this to the other side and solve for T, this is T 1/2, which is half-life. You get T half-life is equal to the initial concentration over 2K. And that's the equation for the half-life. Just a little note here, on the AP exam on the green sheet, they only list the half-life equation for first order, not for 0 or second. And so on the AP exam and on my tests, I will only ask about the half-life for first order. But on the worksheets and in our notes, I'm going to give you all 3 of them just so that you have that for college. Okay, let's look at first order. First order reactions mean that the rate varies directly with the concentrations. If I double my concentration, I double my rate. If I triple my concentration, I triple my rate, and so on. So let's write the differential rate law. So rate is going to be equal to a constant times the concentration of your reactants raised to the first power. If I were to graph this, if I'm graphing rate versus concentration, I would get a straight line. Because like I said, if I double my concentration, I double my rate, I triple my rate, and so on. If I wanted to relate it to time, I would need to graph natural log of A, and I would get a line that looks like this, where the slope is equal to -k again. For the integrated rate law, what I would do is I would plug this into y equals mx plus b. So my y is natural log of concentration at a given time is equal to my slope, which is negative k, times my x is t, plus my y-intercept would be natural log of the initial concentration of A. And that's my integrated rate law. For the half-life, this is first order, that's the one that you need to know. Remember we said that at the half-life, this is half of what it was initially, and we're going to call T1 half. So we're going to plug these into my equation here. So we're going to say natural log of A naught over 2 is equal to negative KT 1 half plus natural log of A naught. And if you do some math to solve for T1 half, you'll get that T1 half is natural log of 2, or natural log of 1 half, which is 0.693, and then over K. That's the equation that you will need to use on the AP exam. Let's look at second order. So second order means that the rate varies as the square of the change in concentration. So for the differential rate law, it's going to be rate is equal to K times the concentration of A squared. If I were to graph the rate versus the concentration, it's going to be an exponential curve. If I were to graph it in terms of time and I want it to be a straight line, I would have to plot 1 over the concentration to get a linear relationship, and it would look like this, where the slope is equal to K, positive K, not negative K in this case. If I wanted to integrated rate law, I would put this in the form of y equals mx plus b, so my y is 1 over the concentration at a given time, equals to my slope, which is K, times my x, which is t, plus my y-intercept here is 1 over the initial concentration of A. For the half-life, we're going to say it's 1 over the initial concentration over 2 is equal to K T1 half plus 1 over the initial concentration. And if you rearrange this, you get your half-life equation to be 1 over A naught times K. Again, the half-life equation for 0 and second order, you would use those in our notes and on our worksheets, but on the test and on the exam, we're only looking at first order half-lives. Okay, units for K. Units for K are pretty important, and you can either memorize them or come up with them. You know I don't memorize, I come up with stuff, but it's totally up to you. I'm going to show you how I come up with them, and you can, like I said, memorize them or come up with them. So for 0 order, rate is equal to K times A to the 0, which ends up being equal to K, right? So K is going to have the same units as the rate, because rate is equal to K, and rate is going to be molarity per time. So those are the units for 0 order, molarity per time. So it could be molar per second, molar per minute, molar per hour, molar per day, any units of time. Let's look at first order. So rate is equal to K times the concentration of A to the first power. So let's think about this. So my rate is molarity per time is equal to K times the molarity. So if you move this molarity to the bottom here, so you can solve for K, your molarity and molarity cancel, you end up with K is equal to 1 over time units. Let's look at second order. Second order rate is equal to K times A squared. So my rate, which is molarity per time, is equal to K times molarity squared. So if I move this molarity squared to the bottom, I would get that K is equal to molarity per time times molarity squared. This cancels with 1 over these, so I end up K being 1 over molarity times time. So these are the units. Again, you can just memorize them for 0, first, and second order, or you can come up with them the way that I just showed you.